Thank you, Mr. Ostertag, for the very nice introduction, and also to the organizing committee for giving us the chance to present some of our work we've done in the last year. As you can see from the title, it's all about protecting our everyday food. Now, I want to show you an opportunity where we combine surface-enhanced Raman scattering, which is abbreviated SERS. It's a technique to increase the signal of the Raman scattered material. And we want to combine this with a portable Raman spectroscopy to take an application out of the lab into the real world. The motivation behind doing this work is that substances, potentially hazardous substances, can enter the food chain and they can have a significant health impact on consumers. Now, significant can range anywhere between mild digestive problems all the way up to death, which is a pretty significant impact. The biggest problem with these hazardous substances is that these effects can occur even at trace levels of the material. So even if you have a very, very small amount of hazardous material inside your food, you can have suffer from severe impacts. The good news is that most of these hazardous substances to humans or animals are strictly monitored already within the food chain in laboratories and are usually legislatively regulated. However, the food chain is a very long, very open food chain, very long logistics chain also, and these substances can enter anywhere. So from the field where you grow plants, from seedlings that get handled in companies that may be exposed to chemicals, all the way to fruits that may or may not be impregnated, all the way along the logistics chain, from packaging all the way to the supermarket where you buy them. And then it's your own responsibility how you handle the food. So that last part is fairly secure. The biggest problem is that for testing on hazardous substances, often complex procedures are required, or it is very time-consuming to make these measurements. If you think about, for instance, a microbial testing, then if you take a typical piece of poultry, chicken, it gets passed along the supply chain within anywhere between 8 and 18 hours until it hits the shelves of your local supermarket. But the microbial testing takes about 3 days. So it's a bit keeping your fingers crossed that really the meat that you've eaten yesterday hasn't been infected. If it has been, you start rolling up the entire supply chain to find the possible place of contamination. But this is very tedious work. And often this requires sophisticated equipment and people using it. If we stick to the microbials, it takes a graduated biologist or a food chemist or food biologist to prepare the samples, incubate them for 2.5 days, and then sit down for a couple of hours with a microscope and count the tissues, the samples. So it's really very tedious work. Now, we think that Raman spectroscopy can aid here because it allows potentially quick and easy testing without a lot of sample preparation. You just take your Raman spectrometer, place the probe in front of the optics, and you conduct a measurement, and you have the signal more or less immediately. And we're talking about typically times less than a minute. And then the next idea is, how do we take this application into the field? The key for taking the technology to the field is having the measurement contain enough physical information. Professor Kessler has explained this to us yesterday in very great detail. If you can do as much chemometrics as you like, if the signal is not in your measurement, you have no chance of finding it back. So these low concentrations of materials give you a very small signal, and without artificial signal enhancement, by physical means, there's usually no way of detecting them. SIRS is a relatively well-known technique, rather expensive on single-use substrates so far. We targeted these substrates about 2 years ago to check if it would be able to drop down the cost by applying techniques of mass printing and existing nanoparticle SIRS technology. We print our SIRS substrates on a special material. We then cure, cut, and fix these the substrates to carrier slides for better handling. Our process allows to use the conventional gold or silver-based nanoparticles. The key to really taking this measurement, especially silver nanoparticles, to the field is to control the oxidization process, which kills off the efficiency of the substrate. And this is the reason why we have had Maya also named as first author, because we've reached a breakthrough here which controls and hinders the oxidization process, especially in the silver substrates, so we can achieve shelf lifetimes of our substrates, which currently are lasting for 9 months, respectively 3 months for silver. And this is limited currently by the testing period. So at the moment I can tell you these samples perform as well as on the first day. And we've commercialized the product, the silver substrates just recently, and the gold substrates about half a year ago. They look like this, so you have a small region where you can drop your analyte onto, and for better handling we've mounted this to a microscope slide. Okay, these SIRS substrates can be used with any type of existing Raman equipment. So whether it's a fiber-coupled Raman system consisting of a laser, a probe, and a spectrometer, or an integrated Raman system which also contains a spectrometer, an integrated laser, and a bit of optics here. I've shown this instrument for a good reason. This instrument contains a feature we've introduced to the market last year, which we call Raster orbital scanning, which again enhances the signal of a Raman measurement. If we have a little look at this, how it works, we make use of the complete statistics of our substrates. Now the material that we print on consists of a fiber layered material, so if we print the nanoparticles onto the substrates, statistically they form regions where SIRS radiation gets enhanced, which is a so-called hotspot. It's indicated here by the red dot, and if your laser beam hits such a spot, you will get a signal. The question is, how do you increase the signal? Now you can cover a larger area with a wider beam to get your signal up. The problem is this will also increase the range of angles in the system. So if we sweep a tightly focused beam over this area, statistically we hit more hotspots and we increase the signal. At the same time, we move the tightly focused beam over the sample, which means we distribute the heat load of the sample, which leads to a reduction in the background signal. And furthermore, because we work with a tightly focused beam, it also reduces the range of angles in our optical system, which gives us a better resolution. And then we end up with a much better signal quality, as indicated here on the bottom. Now, we have applied a number of analytes that are often hitting the food chain. The first and most pronounced one is melamine. Melamine is a substance which is used to suggest higher levels of protein than are actually present. Typically tests are conducted with testing just for nitrogen. Melamine contains a lot of nitrogen and thus suggests higher levels of protein for standard testing. The problem is melamine is hazardous. And in 2007, in the US, Menu-Food had the substance entering the pet food chain, which led to thousands of pet animals in the United States and Canada being affected. Not even a year later, we saw images like this in the media, where when in China, milk powder was infected with, or was mixed with melamine. The numbers here are quite significant. So more than 300,000 infants have been fed with this milk powder, which led to more than 50,000 infants being hospitalized. And then, thanks to the effort of the medical staff, but still 6 of them died. So it's a pretty severe impact, especially for the affected families. I should also mention that 2 people that were held responsible for this also died after being sentenced to death in China. The economic consequence was that milk powder from China may not be imported into Europe anymore. In Europe, we have a strict Commission regulation from 2008, so the European Commission acted relatively quickly. Any sample that contains more than 2.5 milligrams per kilogram of melamine inside the food chain must be immediately destroyed. If we translate this to relative units, we're talking about ppm, so parts per million level of this substance. So we're really talking about trace amounts. So we've checked, can we, applying SIRS and our Raman instrumentation, identify this at ppm level? And I want to show you some data. So this curve shows you the raw signal, the Raman signal, and in black, the dotted black line gives the spectral response of the unloaded substrate. And if we dope the substrate with melamine at different concentrations, you can see these prominent spikes here at around 700 wave numbers Raman shift, and there's 2 small peaks here between 12 and 1500 that are used for the qualification of melamine in the substance. And here, if you want to have a closer look at the concentrations of interest, you can see that this still differentiates significantly from the background. Now you may ask, why are these lines below 0? The reason is we did this measurement under ambient conditions, so without shielding. These measurements took a second, and this is how your solar irradiance changes in the lab. The solar spectrum changes in the lab from 1 second to the next when a cloud passes by. The next question is, if we look for a number, we don't only need to qualify that melamine is inside the substance, but how much melamine is inside the substance. So if you want to do quantitative analysis, your sample needs to be very reproducible. And we've produced a number of these batches and just taken random samples for the source substrates from these batches. And we found a standard deviation of about 3.5% over the batches. And I've shown a bit like the best and the worst, the blue and the green, of these samples. So the good news is we're not only able to qualify, but also to quantify these. And this is something else that's relatively new to SIRS applications, is that you can also quantify the amount, because previously substrates used to be pretty inhomogeneous. If we stick in the food chain and we move away from milk powder to the livestock that is producing the milk, we find another chemical that may be used. It is Enrofloxacin, which is a broadband antibacterial agent, which was banned for use in poultry worldwide in 2005, but is still used in aquaculture today. So it is used to protect livestock and our aquaculture farms against E. coli or especially methicillin-resistant strains of Staphylococcus, and this is quite frequently used actually in agriculture, in aquaculture. Here, not the EU leads the way, but the US and Canada, they've banned this. In Europe, there is a quantification limit, which is the detection limit, which is in the orders of micrograms per kilogram for tissue. So if your shrimp contains more than 10 micrograms per kilo of enrofloxacin, you may not eat it, or it may not enter the food chain. In milk, because it's easier uptaken by the body, this limit is lower. If we look at the data, so we've dropped the appropriate concentration of enrofloxacin onto the substrates, interrogated it, and you can see very nicely these prominent quadruple spikes here, and then the set of lines down here, which is the spectral signature of Enrofloxacin. This measurement takes a little longer, to be honest, where we've worked in the order of seconds, a second, 2 seconds exposure times. It takes about 40 seconds to interrogate the sample and to achieve the desired and requested signal-to-noise ratio. But still, this is, for this sample, it's mission accomplished. If we stay in aquaculture, so here looking at shrimp, yeah, and just to give you an idea how aquaculture looks, it may be a pond, it may be a bucket, but then the water is relatively still, and especially in warm regions of the Earth. So all these ponds are also susceptible to fungi growing in these plants. A typical fungicide that is used in aquaculture is malachite green. It has it's a dual function material. It's a fungicide as well as a pesticide, and people just drop it into the water. The problem here is that it attaches very well to body fat and stays inside the fatty regions, especially of fish, and you can you can still detect it long after fish have been exposed to malachite green. So a half-life of about a month and a half is pretty significant. It may not be used in Europe, but it is used outside the European Union. So for Europe, we have a strict detection limit of 0 microgram per kilogram, which means that we have to achieve analytical accuracy of less than 1 part per billion. Now, if we look at the raw data, we've worked with somewhat higher concentrations of malachite green that we dropped onto our substrates, and we're still about an order of magnitude, 2 orders of magnitude away from where we need to be. So we're almost there, and we're currently working on getting this fixed. Moving away from aquaculture, we move to agriculture. Here, agents are typically delivered to the field by spraying, whether it's ground-based from a tractor or spray painted by a crop duster. The substances usually stick to either soils or the leaves, and often combinations of agents are used. As the last application, I want to show you results we've made on Theorem, which is a very frequently used substance in agriculture. Theorem is a broadband fungicide as well as a repellent for snails and small animals that start eating the trees, the wood of the trees or the roots. It has a second function. It can also be added to the meat in the meat chain, similar to melamine in milk powder. It suggests higher protein levels on standard nitrogen testing. The problem is Theorem is a nitrosamine cursor, and if it hits oxidants inside your body, it produces nitrous amine, which is known to increase the risk for cancer. The exact metabolic impact is currently under study in the REACH Institute in Sweden. It is allowed in most parts of the EU, so most meaning all except Germany and the UK, where we have in Europe we have a 200 ppm concentration limit. In Germany and the UK it's banned, so we're again facing very low amounts that we need to detect. And if we drop ppm concentrations of Theorem onto the substrates, we can very nicely see the peaks that are used for qualification and also for quantification. So this one, finally, again, is mission accomplished. Over the last 19 minutes, I've given you a brief insight in why we think Raman spectroscopy is relevant for looking at food-relevant materials. I've introduced our gold and silver nanoparticle-based substrates. I've shown you that the substrates can be interrogated with a number of already existing instrumentation in the market. I've briefly discussed a technological feature of one of our instruments, and I've shown 4 different applications. And compared to yesterday's soccer match, which ended 0-3, we have a 3-1 record here, and we're working on getting that last goal as well. As it was said in the introduction, I am standing on the shoulders of giants, so all of this work would not have been possible without Maya, who had the brilliant idea how to limit the oxidization of the silver nanoparticles, which is something I will not tell you. And then my colleagues Cleo and Derek, and of course the division head Adrian, for providing these great substances, allowing me to actually solve this market application and conducting all of this testing. And I'd like to thank you for your attention.